So hello everyone, my name is Alister. Today I'm going to talk about my work called ShaRP, Shape-Regularized Multidimensional Projections. In this presentation, we're going to start by giving an introduction to what a projection is and what's the need for projections. I'm going to motivate the use of shape regularization, which is the main contribution of my method. I'm going to talk about how we developed ShaRP, and then I'm going to talk about some aspects of its evaluation and pointers for future research. So first of all, projections. So projections are all about visualizing high-dimensional data, and by high-dimensional here we mean data that lives in more than 3 dimensions, but usually what's going to happen is data is going to live in way more than that, like in tens or thousands of dimensions, and a direct representation for such data spaces is either impractical or impossible because we only have so many visual variables to use to represent each data dimension. And in a way that allows people to actually understand the patterns of the data being represented. We can also resort to indirect representations. So here, for example, I'm showing a parallel coordinates plot. And here underneath, I'm showing a scatterplot matrix. So these are fine, but they're also limited. A scatterplot matrix only shows you pairwise relationships in the data variables. A parallel coordinate plot can only handle so many dimensions and so many data points before things start getting cluttered. And projections are therefore an alternative for all that. And in a projection, what you do is instead you have a projection function P that takes this data that lives in n-dimensional space into a q-dimensional space, where q is usually very, very small, like way smaller than n. And for example, if we use q equals 2, which is the case we're going to focus on, we're going to obtain scatterplots. Here to the right side, you have TSNE being shown when applied over the MNIST dataset, but you can also use another algorithm for that, such as UMAP, and there are many other algorithms available to perform projections. And then you visualize the data patterns by projecting it first and visualizing in a 2D screen. On the perceptual side, though, it's important to notice that humans do not take in the scatter plots that we have just seen point by point. We perceive overall the visual patterns in these scatter plots, so grouping of data points, interspacing of data points, shapes of the clusters that emerge. We might use different variables to color them, and then that's going to create different visual patterns. And these patterns are, of course, derived from data, but they're not only derived from data, they're also very much related to the algorithm that generated the projection. And that means, for example, that TSNE has a recognizable way of laying out points in space. UMAP has another way of laying out points in space. VCA has another way of laying out points in space. These recognizable ways of placing these points in space is what we call visual signature. So if you think about TSNE lays things out roughly in a circle, where inside that circle you have these little like jigsaw puzzle-like pieces that interlock with each other. While UMAP, for example, is going to have clusters that are very tightly packed together and very distant from each other. What we have observed then is that visual signature is important because it exists at this level at which humans take in projections, but it's not directly controllable. For all these algorithms that we're used to, it is usually a consequence of algorithm design, and it's a very indirect consequence. So because we choose to use some modeling for the data, we get a type of visual signature. Because we initialized the algorithm in such a way XYZ, we get a specific visual signature. Also, not only on the perceptual side that we were just talking about, but also for some specific task, we might benefit from having a specific visual signature show up. And I'm going to give more details about this later. What we contribute with, the main contribution of ShaRP, is to put this shape aspect, which is part of visual signature, it's an emergent visual feature, directly under the user's control. So the user can define the visual signature of their own projection with respect to shape. So this is what we want to do with ShaRP. And how do we do it? Let's dig into how this algorithm actually works. And we're going to start by looking at a very close relative of ShaRP, which is SSNP, some work by Machado and collaborators. And SSNP is an algorithm that uses a neural network to learn a projection of some data set. So by using this hourglass kind of encoder-decoder architecture with two neurons at the bottleneck, we can obtain, by using this bottleneck coordinates, we obtain this type of projection, so this type of image. And what's really happening here, just in a simple way to understand, is that you have an autoencoder. So this part that's now highlighted is a vanilla autoencoder, input and reconstruction. And on top of that, what you're going to have is this separation inducing component, which tries to recluster the data. So it uses a cross entropy loss to try to match a predicted label, here represented by y hat, to these labels y bar, and I'm calling them y bar here because this can also be pseudo labels as derived by a clustering algorithm, for example. So you don't need necessarily access to some sort of ground truth here. You can use a clustering algorithm on your data and ask SSNP to reproduce the clusters obtained by that clustering algorithm. And if we analyze the visual signature that we obtain using SSNP, this is what we can see. First things first, the clusters are kind of elongated. They spread out from the center of the projection towards the borders. Because of that, you get some wasted white space. If you think of this shaded region, very little of it is actually being dedicated to representing data points, and this can make the user think that there's like anisotropic aspects to the data, and that the data is linear, and also it just wastes white space that could be using to better represent this data. And last but not least, some groups actually collapse into these line-like structures where if you want to, for example, interact with it, like using a hover tool to see what kind of data point gets projected there, because everything is so collapsed, it's going to be very difficult to interact with. So overall, the visual signature of SSNP fails to achieve high quality. And it's very recognizable. These starburst patterns kind of reappear whenever you use SSNP. So enter ShaRP, enter our idea for a new projection algorithm. The big difference here is that we are kind of like SSNP, but we change the middle layer, the bottleneck layer, to use sampling. And we add an additional loss there to regularize this new sampling distribution that we are introducing towards a given prior distribution. So the sampling distribution is a hyperparameter. The prior that we regularize towards is also a hyperparameter. So for example, here you can think that we are going to learn for a given projection that we want to produce, we're going to learn using the distribution that is an independent Gaussian, so a 2D Gaussian with independent coordinates, so 0 off the diagonals. We're going to regularize it towards the standard Gaussian distribution in 2D. If you think about that, if you look at only this part that is highlighted again, this is just a variational autoencoder. It's input and reconstruction with sampling halfway through and a regularization loss. And here, because we introduced these new hyperparameters, D and P, we noticed as we were developing this that the choice of the sampling distribution has a direct impact on the cluster shapes. Because if, for example, here, again, the example where we regularize things towards a standard normal distribution, and we sample from normal distributions, we expect the samples to be drawn from things that looks like ellipses. Why? Because the equidensity contours of Gaussian distributions are ellipses. And in this case, they're going to be axis-aligned ellipses because we are using independent Gaussians in this specific example. So what can ShaRP do, and how did we evaluate it? So first of all, ShaRP allows you to shape things to your heart's content. And there's a little asterisk in there that I'm going to explain very soon. But for example, if we substitute the Gaussian distribution that we were just looking at for a generalized normal distribution, which is basically a Gaussian distribution plus this new shape parameter that's being called omega here, and we regularize it towards the standard generalized normal distribution, keeping the same omega parameter, what we're going to get is clusters that are shaped like rectangles or squares. Why is that? Well, if you plug in omega 0 there as 2, if you make this equals to 2, then you just get a Gaussian distribution. But as you increase omega 0, instead of getting bell curves in your sampling, you're going to start getting something that gets closer and closer to kind of like a box filter looking like function instead. And this is what makes the sampling get like these rough edges instead of being like smooth around them. So instead of ellipses, you get rectangles. Another thing you can do is to use a Dirichlet distribution and take samples of this distribution and use as barycentric coordinates of a triangle, for example. And then on top of that, you can apply rotation, translation, scaling, and you are going to recover clusters that look like triangles. So here, for example, I'm going to highlight just a few, but it's quite evident that these are shaped like triangles. And the prior distribution that we regularize towards is the kind of like uniform distribution on the triangle, which is Dirichlet with all the parameters set to 1. And well, just to be completely clear here, why do we have the asterisk there? Well, as you've seen, for each shape that you want to produce, you require a specific sampling scheme. And if you go too crazy with your shapes, you're going to need complex sampling schemes to be able to reproduce them. And you need to be able to calculate log probabilities fast. Otherwise, your training process is going to take too long. So if you have a sample of the 2D space, you need to be able to calculate the log probability of sampling that in order to be able to calculate the regularization loss, which is a KL divergence term. So what about the metrics of this algorithm? Well, for the recommended usage that we say in the paper, which is setting beta equals to 0.1, which is represented here, there is a small penalty to quality metrics, but this is expected. It's expected because we are forcing things to conform to shapes instead of just allowing the kind of best projection to be learned. So we are interfering with what could be like the natural finding of a lower cost projection and a higher quality projection in order to produce shapes. And of course, the stronger you make the shape regularization, so if you make beta come closer to 1, you're going to incur bigger penalties in your quality metrics, and that is reflected visually in this type of plot. If you focus on beta equals 1.0 for a moment, you're going to see that this is basically noise, and this is a bad quality projection, so you shouldn't do that. Again, what we recommend is to use beta equals 0.1. This has given us consistently good results as we were experimenting with this work, and you can see here that this looks actually quite nice. Another thing we can do with this algorithm is to do hierarchical data visualization. And for example, by using a self-similar shape for sampling, what we can do is zoom in to specific parts of the projection and recluster it or re-project it using a different variable, for example, as label information, as pseudo-label information, and get something that kind of fills up the same space, splits into the same type of shape, and allows for this nice hierarchical navigation. This is all that we have done. And what next? What do we envision for this algorithm in terms of next steps? Well, we would like to research the effect of this new way of creating projections on user perception. We would also like to extend this algorithm to be able to handle categorical data. We would like to explore the possibilities of using these new hyperparameters to encourage some other desirable projection features, or using more sophisticated architectures because currently it's just a feed-forward neural network, and also investigating the inverse projection capabilities in terms of the generation of decision boundary maps. I would like to thank you for your attention to this presentation. The code is available in the link below, and that is it. Thanks a lot.